look up at the night sky and see a calm, silent tapestry. But up close, that stillness is an illusion. Every point of light is a boiling expanse of plasma caught in a continuous, violent struggle. This diagram illustrates the internal mechanics of a star, which is dictated by two opposing forces. Gravity constantly crushes matter inward toward the core, and that immense pressure triggers nuclear fusion, which releases colossal amounts of energy that push outward. As long as there is fuel for fusion, these forces remain locked in a perfect stalemate. The outward radiation matches the inward crush of gravity. This exact balance is what gives a star its shape, its stability, and its light. Eventually, the hydrogen fuel at the core is exhausted. Without the outward pressure of fusion, gravity wins instantly. The star's crust collapses inward at a fraction of the speed of light, resulting in a supernova explosion or the formation of a black hole. The structure of our cosmos isn't fixed. Every shining object we can observe is just a temporary pause in an ongoing battle between physical forces. That temporary pause is entirely responsible for our existence. Earth's mild climate and liquid oceans rely directly on the steady equilibrium of our Sun, which has bathed our planet in a consistent stream of energy for over 4 billion years. A vast amount of that ancient solar energy, along with atmospheric carbon, was absorbed by organic life and buried deep underground. When we mine coal, we are hauling the physical weight of hundreds of millions of years of stored solar energy back to the surface. This chart tracks atmospheric carbon over a geologic timeline. For 500 million years, the Earth buried carbon, creating a stable atmosphere. By extracting and burning that fuel, we are releasing hundreds of millions of years of trapped greenhouse gases in a few short centuries. When the atmospheric balance breaks, the Earth undergoes a natural reset. Throughout history, shifts in carbon and temperature have triggered massive glaciations, covering entire continents in ice and driving widespread extinctions. The stability we rely on to grow crops and build cities is a fragile chemical balance, and the current rate of carbon release is pushing that balance beyond the Earth's natural capacity to regulate it. If human consumption disrupts the balance on a planetary scale, we have to look out into deep space to see what happens when gravity completely overpowers energy. When a massive star dies, gravity compresses its core into a space so small it has no physical dimensions. This is a singularity. Here, matter is infinitely dense. The gravitational pull traps even light, and the standard laws of physics stop working. Astrophysicists, analyzing the math of singularities, realized the equations work in reverse, which led to the hypothesis of the white hole, a theoretical object with zero internal mass that cannot be entered, only violently expelling matter outward. This diagram illustrates the prevailing theory of the Big Bang. At the very beginning, all space, time, and matter were expelled from an infinitely dense point. Mathematically, the birth of our universe perfectly mirrors the eruption of a supermassive white hole. The relationship between matter and these cosmic extremes became clearer when theoretical physicists like Stephen Hawking demonstrated that black holes aren't completely black. Over vast stretches of time, they leak radiation and slowly evaporate into nothing. A black hole consumes everything until it evaporates, and a white hole expels everything to create a universe. They are the absolute limits of physics, total destruction and total creation. This creates a severe problem for physicists. If a black hole swallows a star and then eventually evaporates away into nothing, what happens to the physical information that made up the star? According to the fundamental rules of quantum mechanics, information cannot be destroyed. If the state of a particle is lost completely, our entire understanding of physics unravels. This diagram visualizes the holographic principle. As an object falls into a black hole, its physical form vanishes, but its quantum information is preserved on the 2D event horizon. This implies our 3D universe galaxies, planets, bodies might simply be a holographic projection of that data. We assume the physical objects we can touch and see are the baseline of reality, but the deeper we look, the more it appears that matter is just a temporary projection of preserved data. To grasp our actual place in this reality, we have to look past the equations and launch physical probes into the dark. We send fragile machines out into the solar system to observe how these cosmic forces play out in our own neighborhood. When we look at Saturn, its massive ring system looks like a permanent fixture. In reality, it is an active collision zone of microscopic dust and ice that is slowly draining into the planet. In a fraction of cosmic time, the rings will vanish completely. Further out, on moons like Titan, we find oceans of liquid methane and nitrogen-rich atmospheres. It is a frozen primordial landscape containing all the raw chemical ingredients of early Earth, just waiting for the temperature to shift. And right next door, on Mars, a robotic arm scrapes a barren surface where water once flowed. Without a thick atmosphere to trap the sun's heat, the planet's equilibrium collapsed, leaving behind a frozen, dead rock. From the rapid expansion of the Big Bang to the slow, final evaporation of black holes, the universe operates as a one-way thermodynamic engine. Things are created, they exist in a temporary state of tension, and then they degrade. The liquid water, the breathable air, and the biological life we experience on Earth rely on a highly improbable set of conditions. We exist in a brief, delicate stalemate between massive forces, a fleeting window where the balance holds just long enough for us to look up and understand it.